Generally, when you talk about search radar, you imagine some antenna like this, some half-cut parabola, and then around the axis it keeps rotating. So this is a sort of picture you get for an search radar. Whereas for a tracking radar, the search radar, let us say, has picked this is a PPI, plant position indicator, and it has located an enemy aircraft, say, east of the radar. This information goes to this is a search radar, and from search radar, this information goes to the tracking radar. Now, the job of the tracking radar is it's not going to rotate 360 degrees. It just scans in this particular sector and tries to accurately pass on the information to the missiles. Once the missile gets this information, it rides over this particular path and then tries to destroy the target. So that's how the tracking radars work. They are limited to a particular sector. They can be positioned in any sector, but their scanning is limited to that particular. So it's sort of oscillatory motion. Okay. Left and right, you keep scanning in a particular sector and try to capture the information accurately. The first one, which was type of radar which was developed, is called conical scanning. So imagine you have you're holding a pencil in your hand and you try to rotate this pencil. Okay, so that's how a scanning radar, conical scanning radar works. That is the axis. You have a common axis, and around the axis you try to rotate the beam. Okay. I think the next one will make it clear. So this center point, are you seeing the next slide, Sahana?
Yes, sir. Amplitude modulated wave.
Amplitude modulated, good. Okay. So this is the axis, but now at different instance of time, I'm just drawing the two-dimensional figure of the radiation pattern. Okay. So you keep moving the radar in this fashion, in a circular motion around a common axis. So what's going to happen is, whenever this particular antenna beam crosses the target, and this happens to be 270 degrees, the signal output is going to be maximum. Okay, and then you keep doing this again like this. Again, zero is somewhere you reached here, and 90 degrees is exactly opposite, so you get a V minimum. Now, once you have this information, then you can feed it to a control system so that the axis gets shifted in this direction. So with time, once uh, or even if you don't shift the axis, at least you know that the aircraft is left of you. Okay. Left in, it can be any direction. In this case, it's simple. So left of you, exactly in the western direction. So you know you can pass on this information to the missiles, and missiles will have their own control systems. So in such a way that maybe sometime later we can even discuss some missile control systems, and then they go and destroy the target. So this is called the so this whole thing is amplitude modulated. Okay. So you'll be able to understand, you make out which direction the aircraft is exactly. And these beam widths are extremely narrow beam widths. Okay. Uh, Unlike the search radar, which had a very large beam width. But mechanically, just imagine to rotate like this is very difficult, quite cumbersome. Okay. But if you look at MiG-21's radars and all, the initial radars were all this conical scanning type only. But there are ways by which this signal can be jammed by the aircraft, because they know the rate at which the tracking radar is rotating, and whenever the uh, tracking radar passes the target, they will intentionally give very high beam, high pulses. Okay, so this will confuse the uh, tracking radar and it will lose track. Once it loses track, then there's a problem. Again, getting it back takes time. So by that time, the enemy aircraft can always take some other maneuver and escape. Presently it's not being used because jamming a conical scanning radar is a well-known technique now. The next development was something called as monopulse radar. So what they did was it's as if like something like instrument landing system. Uh, what you do is initially you transmit beam A and then you transmit beam B. Get the returns. This is the return. If the target is on the axis or on the center line of these two beams, then the strengths of A and B will be A will be equal to B. So you know that aircraft is coming in this direction. But if the aircraft is not along the bore axis, then definitely, like in this case, the return from beam A is going to be much lesser compared to beam B. So this difference is used for estimating the direction of the aircraft. Is it okay, Sarana? Are you getting the idea?
Yes, sir. Yes, sir.
Basically, you're sending one beam at a time, but the beams are off-centered. Okay, so it's in a different direction. So you look for the returns and position your radar in such a way that you get equal returns. So this angle of this radar physically is shifted so that you get equal returns. And once now this is a mechanical shifting, so you can easily measure what is the angle at which the aircraft is coming. So the same information is passed on to the missiles and missiles are fired. An extension of this is called is actually what I have shown you earlier. The previous one is just a two-dimensional thing. So it's just in azimuth, but aircrafts move in three dimensions. So what they do is they use four beams, A, B, C, and D. Okay. So depending on this again is the bore site. Depending on whether the aircraft is above the bore site, this is above. Uh, in this case, it's below, and then you have a right and left of bore site. Okay. Depending on the displacement of the aircraft relative to the bore site, the signals of A, B, and C, D will change. So it's basically one single transmitter, and they use so A, B, C are four different antennas called as horn antennas. Okay, so two-dimensionally they look like this. You all seen horns like loudspeakers. The older generation loudspeakers used to be like this. So they're called as horn antennas. Maybe it's three-dimensionally it will look like this. So these horn antennas are used for taking this decision. Sarah, do you find anything abnormal in the result? Just look at all four cases. Do you find something which you feel is incorrect?
Uh, the last one.
Why? It's open to the class. Okay? Anyone can answer. Something you people have done in your physics lab, in your 12th standard. So look at the position of the aircraft with respect to the bore site and look at the received signals, strength of the received signals.
It's reversed, sir.
It's reverse. Why?
Sir, due to the lens.
Good, good. So there is something called as lens antenna. Okay. So you people have done that candle experiment, no? You get an inverted image. Same thing happens. So there's something called as lens antenna which leads to this. So if it is above, actually you get a, if it is above, it should have been A and B should have been high in the first case. So A, B should be greater than D and C. Whereas what you are getting is the reverse of it. That's because the image is formed in the bottom. Similarly, left and right also have the same issues. Okay. Okay. The last thing in tracking radar is uh, continuous wave CW radar or FMCW radar. Okay, now this is basically radio altimeter. Sarup, why can't I use a conventional radar for radio altimeter? And radio altimeters, as we discussed, is used only during landing. Actually, it is used only during the flaring phase. Okay. Flaring is you have the aircraft following the glide path. So this is the glide path for the aircraft. Uh, the touchdown point. Definitely, it cannot go straight and hit the ground. So it takes an exponential flare like this and then touches down. So it is used only at this particular point, say around 50 feet. I don't remember the exact numbers, but around 50 feet or 100 feet, or maybe 200 feet at the most. So, what do you think will be the problem with the conventional radar? Okay, let's put some numbers and let's see sort of whether you can. Let's say the altitude is even 100 meters, which is quite high, 100 meters. And so this delay, so it's 3 into 10 power 8. So can you just approximately tell me what is the time? So conventional radar, as we have seen, is a pulse.
Microseconds.
Pulse, then we have repeated pulses at PRF, and then it's going to be in microseconds, right? So what is the problem now? So let's assume this is same, approximately 2/3, 0.3 into 10 power. So you're talking about a fraction of a microsecond actually, right? And generally the pulse width is around 5 microseconds, 5 to 10 microseconds. So do you think we can use a conventional radar for such low ranges?
No, sir, because the signal would have reflected further.
That's true. Even before the starting of the, let us say this is the transmitted portion and this is the received portion. Theoretically, the signal would have come already here before the transmitter is switched off. So it's going to be masked. So definitely you cannot use a conventional radar. So what we do is we use a FM modulated continuous wave radar. So it looks, the name looks quite complicated, sophisticated, but it's very simple. So what you do is, generally in radar, if I say 1 gigahertz is the carrier frequency, frequency is constant. Okay, and then you just pulse modulate it. Whereas in radio altimeter, you are going to frequency modulate it. That's why the term FM. So let's say this is time and this is frequency. This solid line is the transmitted wave in which you increase, let us say it is 1 kilohertz to 2 kilohertz. So with time, you increase the frequency. Okay, and then you can't, of course, keep on increasing the frequency. So you then bring it down like a sawtooth. You bring down the frequency and then increase it in a known pattern at a known rate, df by dt. Now what's going to happen is the received signal is going to come back after some time period. Okay. So if you see this, let us say we are looking at a particular, or you're looking at a particular time instant f t1, there is going to be a difference in the frequency between the transmitted and received signals. So this difference in frequency is going to indirectly tell you about the range of the uh, target, or in this case, it's just the Earth's surface. So it will be a good exercise for you people to try to derive this equation, why this delta F should be given by this. It doesn't take much time. You can actually, already the slope is there, you're multiplying by something. Dimensionally, if you look at it, it's correct. Okay, finally you should end up with some hertz. Uh, But why this 2R by C? You can just think about it logically. So that's how you measure the height of the aircraft from the ground by transmitting and receiving, transmitting it with FM wave, and then receiving it back, and then at every instant of time, just measure the difference in frequency, and this difference in frequency is going to give you the radio altitude. Definitely, this radio altimeters are much better than barometric sensors. Okay, barometric sensors have a lot of errors, whereas this radio altimeters are really good and very cheap also to produce. And they are very small, very high frequencies. I think it's around 9 gigahertz. So the antenna size also is very small. Okay. So almost every aircraft nowadays has this radio altimeters. Sarup, are you getting the basic idea of how it works?
So kinda.
Okay. Uh, okay, because in time we are all used to seeing things change in time, so you might feel it's slightly difficult. Okay. This solid line, I'll just repeat it, is the frequency of the transmitted wave. So in time, it's going to look something like this. Frequency is increasing, okay? But amplitude is same. The next portion, after this, you're decreasing the frequency. So gradually it starts expanding. Of course, it's not exactly I'm drawing, but just to give you an idea that amplitude is constant, whereas the frequency is changing. But the received signal will be a signal which is delayed in time, but of a frequency which was transmitted earlier. So you're just using the frequency information as a timestamp in this case. Is it okay, Saurabh?
Yes, sir.
Anyway, go through the book and then you'll be able to understand. So that ends portion on radars. Okay. Uh, Anything you want to discuss on radars? People who are really interested in learning about radars, there's a book, famous book called Skolnick. I think I can probably show you that book. No, I think I lost it somewhere. That used to be our Bible those days. But nowadays people are using this book. It's Richard's. Can you see the book, Saurabh? Saurabh, can you see the book?
Yes, sir. Principle
Yeah.
of matter.
Yeah, if someone is really interested, you can go through this. But it's quite voluminous, okay? Around 1,000 pages. And the other book is Introduction to Airborne Radar. This is also a nice book. In fact, better than the previous one. So in this, if you see this FM ranging and all is given very well. What is 177? So he gives you the basic principle of how it works. And then quite a nice book. This book is quite good. And if you want something very basic, then this radar principles for the novice, or sorry, non-specialist. This is also a nice book, but much simpler. Around 200 pages, explained very well. So all these books are quite good on radars. As long as you are in some job related to aviation, you will always keep coming across these radars. So it's quite important, quite useful also. Okay, so that's all for the day. And next class, we'll start with Sahana's presentation on AMCA. Others can also contribute in making the slides. After that, I'll start with secondary surveillance radars, how it works and all, and then a little bit on electronic warfare. That will be slightly quite interesting. How people try to fool the radars. Okay. So that is basic principles, but I'll show you, I'll give you enough references. Those who are interested in pursuing that topic, definitely you can go through other books also. Tomorrow I'll not be taking the class, so we'll meet on Monday. Okay, Sahana, is it all right?
Okay, sir. Okay,
So
sir.
Monday I expect a good presentation from you on AMC.
Okay.
Okay? Right. Okay then, thanks everyone. Sorry, but bye.